Hey, everybody. This is the fourth of these supplemental lectures that I'm recording. So this is awesome. We're in the final throes. So this one's about system budgets and DFX, or design for X. So as a reminder, these are the recorded lectures, and then we have one more lecture in class. All right. So let's get going. System budgets. Budgets, I know in the real world, budgets are referred to as money only. Like you keep a budget, you keep your money safe and planned out in a budget. It's a little bit similar to that, but system budgets are holistically referred to all the key parameters that are tracked for a system over the life cycle of the system. So all the major reviews, all the even monthly or sometimes weekly programmatic reviews will have a list of system budgets that are being tracked, and even the trend lines are being tracked as it's changing over time and what's happened since the last review, et cetera. So this can be performance, this can be programmatic, this can be a lot of things. So because they're very standard in industry for aerospace systems, there's kind of a set of known or typical methods that are used to describe these, and lots of types of charts, pie charts, waterfall charts, you name it, bar charts, lots of different ways of looking at the data. There's some specific preferences by some customers. I would say, based on what I've seen, there's some typical dashboards, but they tend to be more contractor specific, I think, rather than customer dictated. So there's some flexibility in how you present it, but there's lots of ways you can do it. But it's just something where you want it to be easy to understand, easy to absorb, and consistent throughout all the reviews for the same set of customers, so they know what they saw last time and they know what they're going to expect to see this next time. So given all that, there's a table here that shows kind of typical methods and when they're used. But I want you to know that you are not required for the upcoming reviews to present any detailed budgets. And by detailed budgets, I mean like full page or multiple page analyses that show the outcomes and show how you're doing against certain things like delta V and link budgets and things like that. And I mean detailed budgets, because that's kind of not what this class is for. This class is for systems engineering, and we're learning the general principles of like tracking and how do we communicate and what's important to our customers and how do we present the big picture to leadership and to our customers. So because of that, we're not going to go into all the nitnoid details of the technical budgets, but I want teams to give estimates like you would see in a review, estimated values based on some research you've done, based on similarity, based on some bottoms up estimation, or even some tops down similarity estimation of some of these key parameters. And I'll describe what those are here in a chart or two. So bottom line is, this is a big subject area and there's lots of ways to do it. I'm only requiring that teams have a few estimates of a few of these, which I'll describe in a minute, with the justification for why. And let's just jump into that now. So here are some typical aerospace system budgets. On the left side is space system typical budgets, along with some metrics and some constraints. And then there's aircraft system budgets on the right. What I've done is I've highlighted in yellow the minimum set of parameters I'd like to see you report. And like I said before, not with a full up analysis, but some estimates with some justification as to why that's your estimate for the system you're presenting in SDR. Okay. You may notice there's a margin tracker at the bottom, and I want to highlight that specifically. Good program management principles means you don't allocate all your mass margin, all your cost, all your power budget, and those sorts of things straight away. You hold some back as margin. And actually, the government, in many ways, not in many ways, the government requires a certain percentage of margin at different phases of the program that will slowly be released as you get closer and closer to launch or to fly the asset, or even closer to manufacturing. But certainly in the early design phases, when things are pretty uncertain, there's a pretty hefty requirement of margin to make sure you're going to make those numbers by the end, especially if they're really tight. Like if you need to fit on a certain launch vehicle, and let's say NASA has procured a certain launch vehicle for your satellite, that means there's no flexibility to move to something else. So you have a mass you have to stay within, and they're going to require a pretty big margin, especially at SDR, the very earliest design review. You can allocate like 75% of it, or maybe only 65% of it, and then you have to hold some of it back and then slowly release that as time goes on, because that's risky. That's risky for the government. It's risky for you as a contractor. So I want you to research a little bit some of these margins that are required for the elements that you choose, and show how you're meeting or not meeting those margin requirements for those factors. Okay, so that's system budgets. I'm going to give you examples of this, and this is from something called the University NanoSat program. It's a program actually that some of our students are participating in right now. It's a 3-year exercise. In fact, this month they have their PDR, if I recall correctly. And they operate out of the lab at the end of the 3rd floor of Armstrong. So the one closest to the atrium. There's a lab on the north side of the building. Anyway, so part of the University NanoSat program, they've got some examples in their package where they're describing how to do design. And I'm just going to show you some of the things that they show. So they show, for example, the different components of a nanosat, the estimated mass, the contingency, and you see they built in 25% contingency on top of each element, and then the total mass. And then you have to make sure that your total mass at not just of each element, but at the very bottom still meets the mass requirement. Here's an example of an energy balance. This could be called a power or energy budget per se, and it just shows how your depth of discharge of the battery is not too great, even in eclipse, and how amount of power you need versus power generated is balanced, and so that everything works. This is an example of a downlink budget. A link budget is usually what it's referred to more broadly, but this is specifically a downlink budget. Again, I'm not requiring all these numbers. I'm just showing you an example. A pointing budget and a data budget for the data management system. So these are here just for your perusal in case you're interested. Now, I want to go to our second subject for the day, and that is design for X, or DFX. What is it? DFX is a family of design principles where X represents an element, something important to the life cycle of the system, a quality, a constraint, a life cycle phase that is crucial to understand and early in the design process and not after. And these are principles that have been learned over years and years of designing things, where there have been oopses later on that it's like, man, I wish I would have designed this differently to account for something else. And here we're getting to key factors like safety and life cycle cost and maintenance downtimes, environmental impact, reliability, a lot of factors that get solidified during the design phase. And so the goal of DFX is to make us aware of it and make us very conscious of it and design those things in early, so we're optimizing the system holistically. Okay, I'll talk a little bit more about it in a second, but this is just an example of some life cycle phases where you would have this focus, but that's where the impact is felt, but the DFX focus needs to be much sooner. But this is just when you look at phases of a program and where these things are felt, if you did or did not do it. So let's talk about the design for X, or DFX family. This is a huge list. I'm going to let you review it on your own, but just know that there's so many factors that good designers and good systems engineers especially have to think about well in advance during the design phase to make sure that the system is optimized for these things. Designed for manufacturability, assembly, producibility, reliability, maintainability, serviceability, environmental sustainability. Designed to cost, or cost as an independent variable. Designed for safety, testing and verification, quality, human factors, modularity, disposal, and end of life. I'm sure there are more here. These are some of the more prominent ones, and just wanted to make you aware of those. And here's some questions you can ask as you go throughout. But let me go to now where I want your head to be at, particularly for this review, because while we could spend weeks of lectures on these different elements, there's not much time. DFX thinking is holistic thinking, which is systems thinking. And we've been talking about systems thinking. We've been talking about holistic thinking. So I want you to just clue in and cue in on that. So one example is, imagine you hand your design to the factory to build. What would they complain about most? That complaint is your X. That issue that you have created by your design is your X. And the point here is you need to be thinking about that X before you hand it to the factory. So another way to think of it is that every DFX is a stakeholder requirement in disguise, and there are many stakeholders at many phases of a program. So if it's a safety, design for safety, you've got some regulatory agencies. Design for sustainability, you have others. Manufacturability, you think about all the people affected by whether or not you have done a good job in your DFX, okay? This is really thinking holistically about everything. And so this is an area I get really excited about. We haven't had a lot of time, unfortunately, to cover this. So this is kind of at the tail end, and I'm not going to require much. But I want to go through the reasons why it's important. So we talked about the Mars Climate Orbiter already, and that had some DFX issues. But let's talk about another couple that were very, very serious issues because DFX was ignored or conflicts were not properly resolved. So first one is a very sad story of Boeing 737 MAX. There was a conflict between design for cost and design for safety and design for human factors, honestly. There's this system called the MCAS system that assumed a single sensor input and overrode pilot's response, okay? And the crew was unaware of the MCAS, and training was reduced to cut cost. And even when the training kicked in, the system did not respond, and there was a freaked outness, and more problems happened, resulting in 2 crashes and 346 lives lost, which is awful. The design decisions in this case of 737 MAX favored design to cost or design for cost over design for safety. But the DFX issue here was that there was a conflict, and there's always a conflict. All these DFXs are in tension. They're kind of competing for our attention, right? And if we don't prioritize them properly, and safety should be right there at the top, then we have to do something about that. We need to resolve that. We need to just not ignore it. So those trade conflicts should have been exposed earlier. Just kind of running past it resulted in lives lost. Let's go to another side. F-35 has an ongoing maintenance disaster, or it's just built a lot of cost into the system because of maintenance decisions. They broke down in design for maintainability. There's some bolts, some specialty bolts that require 6 hours to remove. The access points are not thought of with DFX thinking. If you look at this, the aspects here, the technicians must remove 13 panels just to access a simple avionics card. And unfortunately, that avionics card needs replacement more frequently than we'd like. The access panels weren't designed for quick removal. And then as you look at just the cost, and by the way, the cost per the cost per hour of the fleet to operate it is a really, really important life cycle cost metrics. Half of the cost is maintenance and downtime of the F-35 right now. And this is supposed to be an advanced system that had DFX built in, but this was a major, major issue that continues to create a nightmare for the F-35 teams. And they're continuing to try to work that off, but it's really built into the system at this point, and they're just cranking out F-35s one after another. So a lot of issues here, and these are some big ones, and DFX was not properly applied or was ignored in large part. Okay, so how can you apply DFX principles to your team's presentation? Okay, there's a couple of things that I'm trying to make it easy because we're out of time. Number one, you can build DFX principles into your requirements. So if you can think about those things that might be most crucial to building into your level 1 or level 2 requirements, build them in, put them in there, and you could even highlight them. I know I've said in the last presentation that you should highlight the driving mission requirements or the driving system requirements, and yes, you should, but not. You don't have to do that exclusively. And especially if you have DFX, I think that makes a really good impression that you're factoring that in very early on. Second thing you could do, it's a little more time intensive, not much. And I think you would learn a lot going through this. And that is, and let me just caveat, this is optional for teams. I think it would be a good thing to do, but I'm not gonna dock you if you don't. Perform a DFX assessment of your system. So there's 3 tables here, and I'll show them completed on the next 2 charts. So the first thing would be, okay, let's look at some of these categories. Let's choose at least 4 that we think are critical or high risk for your design. And this is just first shot, right? As you think about it. Example would be if you have to build a lot of it, the design for manufacturability and assembly becomes really crucial, right? If you're not building that many of them, then that becomes perhaps a lower priority, less crucial. Anyway, so that would be choose at least 4 categories. Then this table 2 here says, now you start ranking on 3 factors that are subjective, risk, difficulty, impact of each of them. And then you identify the high priority ones based on it adding up to 10 of the risk, difficulty, and life cycle impact. And you say, here's where the weakness is, here's a potential design mitigation, and here's what I'm going to do about it. So this is your, this could be a way you approach this if you want. I want to show you a couple examples. One, let's look at a UAS system, long endurance UAS. So some of the attributes are described in the upper left table, and then the categories that were chosen are in the lower left and why they matter for the system. What are the factors that this is just maybe, might affect the design for manufacturability, maintainability, reliability, and safety. Here's an assessment filled out. This is notional. And then here's some potential mitigation actions on 3 of those items that you might consider doing. So this is one example of these things filled out. Now let's look at a space example. So on the, there's the system attributes, you see the 4 categories chosen, you see the assessment, and again, the mitigation actions. So these were actually generated by ChatGPT. I reviewed them. I thought it was a good approach. I asked Chat, what was this approach and where did they get it from? And Chat said that this was this specific, so this set of evaluations has been done for other things, but has never been done specifically for a design to DFX evaluation, but it felt it was appropriate for this application, which I find fascinating, particularly related to a lot of the questions I've been asking it over time. So it's been learning my style and the way I like to think about things, and it felt like this was a really good application for you all and for what we're doing. So that's an interesting factoid in and of itself. Okay, so that's it. That's the last of these recorded lectures. We've talked about a lot of different topics. This one doesn't have a lot of requirements except in this budgets area, and I will summarize that in class and in charts that will be posted later. Okay, thanks a lot. See you later.